Hi everyone, it's my great pleasure today to talk about our newest work, Mastering Atari, Go, Chess and Shogi by Planning with a Learned Model, also known as MuZero. This is joint work with my collaborators, who you can see here on the slide as well. Now let's get right into it. If you have been following our work, you know that we started working on the board game of Go. And ever since then, we've been working on making our algorithm more general. First, we removed the training from human games. Then we extended to other board games, chess and shogi. And most recently, we've been thinking about how to bring the power of this planning and this search to environments where we do not have access to the rules or where we do not have a perfect simulator. We used the widely known Atari domain for this. And the question we asked us was really, what is the minimum that we need for planning, for search? What do we really need to learn and to predict? And the main motivation for us was that we want to predict the policy, the value, and the reward. This is what we use in the Monte Carlo tree search. So let's look at how we build a model that gives us these quantities. Schematically, you can see the Go board here. This represents our history of observations up to the current state. And we can now define a representation function h that projects this history of observations to some hidden state s that we can use in our learned model. Based on this hidden state s, we can, using a prediction function f, predict the quantities that we care about, the policy and the value. Also, we can define another function, the dynamics function g, that allows us to roll forward our model. This dynamics function, given the current state and some action, will estimate what is the next state that we're going to end up in and what reward do we observe along the way to get there. In stochastic environments, this would give us the expected state. Now that we have this tripartite model, we can then use this and roll it forward and forward again in our search tree. And based on the predictions of policy and value, we can guide our search to build a full search tree just in normal AlphaZero, except completely without using any simulator. Now that we have such a learned model that we can use to search, we can of course repeat this process and roll it out to generate trajectories. We interact with the environment, we run our search to get some distribution over visit counts, from which we can sample to select some action, which we then again apply to the environment, enter a new state, search, etc., etc. This allows us to generate many trajectories, and then we can use those trajectories to in turn train and update our learned model. We sample a trajectory and a state in the trajectory from our replay buffer using prioritized replay. And then at the sampled state, we align our representation function h, a map into the hidden space, into the embedding space of our model. And in this space, we roll our model forward, align with the real trajectory using the real actions. This ensures that our model is grounded. And in every imaginary state, we train our model to predict the quantities, the policy, and the value that our search actually produced in the real trajectory. If you then loop this back together, we can use the model that we just trained, put it back in the search to get better estimates, better predictions, use that in our trajectory generation, and the whole loop improves our policy. Now that we've seen the full training pipeline, let's look at some results. First, let's start with Atari, the newest addition to the algorithm. Here we compared against existing state-of-the-art algorithms, R2D2 and Apex. And you can see that with a similar budget of environment frames, we achieved a new state-of-the-art in both mean and median normalized score. We also, of course, evaluated our algorithm in the classical board games, because one of our desires is that when we extend our algorithm, we do not want to sacrifice any performance in all the domains that we can already solve and do. And as you can see here in the graphs, the horizontal line is AlphaZero. We can reach or even slightly exceed the performance of AlphaZero in all of these domains. So that's great, of course, but one of the promises of model-based learning is also that we should be able to use our model to learn more efficiently, to get more out of our data. And so let's see if we can do this as well. In the normal setup that I just described, we use the search to plan based on the most recent observations from the environment, to select an action, apply it, and set a roll forward environment. But we can also use this very same process on existing old trajectories, where we just take the stored observations, we rerun our search to generate new statistics, but then of course, because of the stored trajectory, we cannot change the trajectory. So all we do is update the statistics, update the targets for our policy networks. We call this reanalyze, because we are rerunning the search, we are analyzing again our old data to learn more from it. We then combine this reanalyze with increased replay and the target network to combat value overfitting. And when we run this at a standard setting of 200 million frames in Atari, again we can see that we reach a new state of the art. In terms of median score, we can reach more than 2x higher score than previous algorithms. In terms of median score, it's also more than 1.5 times higher. Currently, we're working on pushing this even further to see how far we can go in very, very low data regimes. Now let's look at a few ablations to understand the algorithm a bit more. Let's start with the classical game of Go, and let's start with how well can our search actually scale with this learned model. One of the great properties of normal Monte Carlo tree search is that it scales very well as we give it more search time. And here we compare our learned model in blue to the baseline that is using the real simulator. And as you can see, even for very long searches up to 10 seconds per move, the model scales very well. Notice the logarithmic scale. This is more than 2 orders of magnitude longer searches than it was trained for. And even beyond that, the performance remains stable. Next, we did a sanity check in Pac-Man to ensure that our Atari results were not due to, say, like a large network or our training setup, but really due to the algorithm. So we took our framework and we implemented Q-learning. And indeed, as we can see, Q-learning in our framework achieved very similar results to the R2D2 algorithm, whereas the MuZero algorithm reached a much higher performance. Finally, we also investigated how does our performance scale as we search more during training. And this is a plot of several training runs in Miss Pac-Man using a different search budget per move. As you can see, as we search more per move, we both learn faster and reach a final higher performance. Interestingly, even with only 6 or 7 simulations per move, which is less than the number of actions in this game, we can reach a very strong final performance. Thank you for your attention. If you want to know more, please scan the QR code for our paper and check out the poster here at this workshop.